Alright, this is section 3.4 on rectilinear motion, page 1 of notes. So when we talk about motion, we're going to be talking about just back and forth motion or movement along a horizontal or a vertical line. Spelled it wrong. Horizontal or vertical line. In fact, rectilinear, think about it, it has the word linear in it, so it's movement on a line, rectilinear motion. So if I was to follow the path of a line, say that line, I might start here, move a little ways this way, move back here, move back that way, move back here. So if I do a bunch of motion on this line, you can't really necessarily tell where I've been, unless you watch me when I go. But that is rectilinear motion. And that motion is represented by a function. The name of the function, or the symbol for the function that we're going to use, is S. This is the position function, and it is a function with respect to time. So S stands for position, and it is in relation to time. So S is going to be the direction, it's two things, the direction and distance that a particular point is from a fixed point, or a pre-identified point, at some point in time t. So it'll nearly always be the variable t here. So S of t would be the position at time t. So the value of S, a position value, say if I get S equals -5, that basically tells me that I am 5 units away from my initial point. Say the initial point was the origin. I'm 5 units away from the origin, and I'm to the left of the origin. Okay, so the sign tells you what direction you are, to the left of the origin in this case, and then the magnitude tells you how far away. Okay, so that's the position. We're going to look at this example. A particle moves along a horizontal line. We'll treat this as our horizontal line. So we're talking about a particle moving along this line back and forth. And it moves according to this position function. So at any point in time t, we can figure out what the position is by evaluating this function. Time is going to be measured in seconds, and S is going to be measured in feet. We want to draw a sketch of the particle's movement. Now if I actually did that, it would be just like the one that I started the page with. It would just be motion along that line. You wouldn't be able to see it. So I'm going to modify the drawing a little bit, and I'm just going to draw each segment. I'm going to move up a little bit to draw each increment of time. So actually what I want to do, let's make a table of my time values. So I'm going to do time for 0, 1, 2, 3, 4, 5, and 6 seconds. And the position S can be determined by this function. So when time equals 0, position is -12. Time equals 1, even that's not that hard to figure out, but I'm going to use my calculator to help me. So my y equals, I'm going to put my function in there. Now it's not going to show up as t. There's no need to even force it to show up as t. We can put the function in just like that. And the easiest way, since I know I just want whole numbers from 0 to 6, the easiest way to get that is just to look at the table. So I'm going to go to second table. My table is already set up to use whole number increments. If yours is not, you can do second table set to establish what the increments are and what the start point is. So I can get my numbers right off of this. So for x is 0, we have -12. X is 1, it's at the position -8. For 2, it's -10. 3 is -12. 4, -8. 5 is 8. And 6 is 42. So now I'm going to plot this. So even though this position function is a cubic function, which would normally have a curve to it like that, I don't want to show that movement along the y scale. I want to show that position on an axis. Alright, so I need this to go from what, -15 to 42. So I'll start -15, -10, -5, 0, 5, 10. Looks like I'm going to run out of space. I'm just going to show a break in my graph. That basically shows that the scale is going to be changed. And I'm going to jump all the way up here to 45. Okay. So let's start plotting some points. I'm going to start t equals 0 at negative 12. So I'm just going to show a point for that. I'm actually going to label my points here, t equals 0. Then at 1 second, I will be at negative 8. So the 1 second point in time, I'm going to get over here. So this is t equals 1 second. And basically, for that first second, I traveled to the right 4 units. So I'm just going to note this here. I'm going to go right 4 units. Okay, my next piece, I'm going to go from the negative 8 position, which I'm actually going to show on the line above, negative 8, and I'm going to move to negative 10. So I'm going to move this direction. And now I'm at t equals 2. And I've moved back 2 spaces. So this, I've moved to the left 2 units. We'll continue in this fashion until we've done all the movements. So to get from 2 to 3 seconds, I'm going to start with my 2 second mark at negative 10. Negative 3 takes me back further to negative 12. So I'm going to continue in the same direction, which is a movement of left 2. And then I'm going to go, for my 4th second, I'm going to end up at negative 8. So I'm going to start here. I'm going to move back over here to negative 8. So that's a movement of 4 to the right for 4 seconds. So there is right 4. And then let's see, after that, I'm going from negative 8 to positive 8. And this is all in the same amount of time. So negative 8 to positive 8 takes me all the way over here. That's t equals 5 seconds. That difference was moving to the right 16 units. Still, in only 1 second, I go that far. It's a little faster. And then from 5 seconds to 6 seconds, I'm going from 8 up to 42. So on this, the way I did my scale, it doesn't look like as far as the last one, but we know it actually was. The distance here is, what I do, I moved right 34 units. So we could actually tell a few things from this. Just from looking at the position at each second, we can see where we moved left, where we moved right, and really how fast we were moving too, because each of these is 1 second increment. So here I'm moving 4 units per second, here's 16 units per second, here's 34 units per second. So my fastest time was between 5 and 6 seconds. Times that I was moving left are from 1 second to 3 seconds. I was moving to the right all those other times. Actually, I want to look at the time from 1 to 3 seconds a little closer here. What if we were asked to find the average velocity from t equals 1 to t equals 3? So you remember average velocity is the rate of change of distance over time. So like average miles per hour in your car is the change in distance over the change in time. So the change in distance we can think about as the change in position, change in s, over the change in time, and I want to evaluate that from time equals 1 to time equals 3 seconds. So if I use my position function for the change in position, I would evaluate the position at time equals 3 minus the position at time equals 1, all over the time difference from 3 to 1. So this is just like our slope formula. It's the slope of a secant line between 2 points. So I'm going to use my table right here. The position at 3 seconds was negative 12 units to the left of our origin. We're going to subtract the position at 1, which was minus 8. All that's going to be over 2. So s minus a negative, so that's negative 12 plus 8, so negative 4 over 2, which is negative 2. Units of measure for velocity is, for this problem, feet per second. So I have negative 2 feet per second. That's the average velocity from time equals 1 to time equals 3. So we did move 4 complete units to the left, so it was negative 4, over a 2-second interval gives us negative 2 feet per second average velocity. The negative part means it's to the left. So the magnitude of this, the 2 part tells us how fast, the negative part tells you what direction. So I'm going to add that to the notes. The negative velocity means a net movement in the negative direction. It wouldn't have to be negative movement the entire time, but the net difference, the net change in position would have to be negative to get that negative value.